Hello, this is Dr. James Camp from Lee College in Baytown, Texas, and this is my presentation on making decisions in the C family of languages. I say in the C family as opposed to one specific language because everything I teach in this lecture pretty much carries across every C family language. It's part of the standard C syntax. So C, C++, C Sharp, Java, JavaScript, all of those use this same decision-making set of structures. Okay, what's the big idea? The big idea of computer decision-making is that once in a while, the flow of your program is just kind of coming along, and it reaches a decision point. Okay, there is some question you want to ask, and if the answer to that question is yes, you want to do maybe operation A. Okay, but if the answer to your question is no, you want to do operation B instead. Okay, you can think of lots of examples of how this works in everyday life. You're going to the grocery store, you find out that the name brand product is on sale, but you ask, is it actually less expensive than the store brand product? If yes, then I want to buy it. If no, I still want to buy the store brand product. And then, of course, after you've made that decision, you return to your normal program flow, and it just keeps on going, regardless of whether you did A or B. Okay. You can think of a computer program example of this if we were doing a guessing game program. If the user guessed high, you'd want to say your choice was too high. If the user guessed low, you'd want to say your choice was too low. We'd have to make a decision there on which of those two outputs to perform. So almost all programming languages have some structure that works like this. If make some sort of decision factor here, then do A, else, that is, if that decision fails, then do B. And that's a pseudocode representation of the flowchart I have on the left here. Okay, so before I can tell you how to implement an if statement in C++, I need to tell you a little bit about the logic behind this, the way computers think about logic problems. And this all goes back to a fellow named George Boole in about the mid-1800s, so long before we had computing machinery, long before we had binary decisions made in ones and zeros. This fellow came up with the idea that there should be an algebra, he called it, of logic. Now you may think, when you hear the word logic, you may think logic is what I used when I was a teenager to convince my parents to increase my allowance, or logic is what I used to persuade my girlfriend that we should go to eat at my favorite restaurant instead of this other new restaurant. That's not the kind of logic we're talking about here. We're talking about logic such as, if X is true and Y is true, then what do we know based on that? And for this logic, there are only two possible values. That being true, which I'm going to symbolize with a T, or false, which I'm going to symbolize with an F. In computers, this would be represented by a 1 binary digit, and this would be represented by a 0 binary digit. Okay, since computers, as you remember, only deal in 1s and 0s. Okay, and there are three basic operations that you can do with these values. And, which tests to see if A and B are true, or, which tests to see if A or B are true, and not, which is simply the logical reversal of a value. So let's explain these with what's called a truth table. Okay, these values and operations come together such that if X is true, true, false, false, and Y is true, true, false, false. Let's see what some of these operations would be. So if we checked X and Y, that's only true if both X and Y are true. So the only situation where X and Y are both true is this first one. So this is a true result. But in the second one, only one is true. In the third one, only one is true. And in the fourth one, they're both false. So all of these values evaluate to false. Okay. What if we tested X or Y? Now, X or Y is true if either one is true. So they're both true here, so that evaluates to true. But in this next case, one is true, so that evaluates to true. One of them is true, so that evaluates to true. It's only this last case where they're both false that the OR operator would return a false value. Okay? And finally, let's just see what the not operator does to the variable X. Okay? Over here, X is true, so not X is the logical reverse of that, false. Here, X is false, so the logical reversal of that is true. Okay? So that explains the three Boolean operators. Okay, how do we use Boolean logic in C family languages? Well, there's actually a type of variable called a Boolean variable, which is type BOOL in most C family languages. I think they actually spell out the word Boolean in Java. And it holds values 1 equals true or 0 equals false. And you can actually use the keywords true and false in C++ to represent those values. You don't have to. So if I had a Boolean variable is this for real, I can give it the value true. Okay, and there we go. That brings to mind one. That's actually a bad variable definition. Usually, usually we define a Boolean variable name so that it can be dropped into an if statement and make sense. So, like, we wouldn't say if is this true. So we might say color is red to define, the state, whether we should stop at a stoplight or not. Okay, and at this point it might be, the value might be false because the stoplight is some other color than red. And so then we could do a question, if color is red, stop, then stop. Okay. So that's generally how we define bool variables, so that they contain a sort of truth content in just the name. If the value is true, then the name would be true. Okay. But let's, for right now, go back to our x and y from the previous examples. So if we had bool x equals true, y equals false, okay, the C equivalent of the Boolean expression x and y, okay, translate that into C, and it looks like x ampersand ampersand y. So this double ampersand is the AND operator in C. And of course, that whole thing evaluates to false because x is true, but y is false, and the AND operator only returns true if both arguments are true. We looked at the Boolean expression x or y. Here we do x pipe pipe y, vertical bar, sometimes called a pipe symbol. That double vertical bar is called the OR symbol. Okay, and of course this one will return true because x is true, y is false, and OR returns true if either of its arguments is true. Finally, we looked on the previous page at the Boolean expression not x. In C++, we use the exclamation point to represent not. So this is the not operator in C++. And it's actually pronounced, C++ programmers are funny, it's pronounced bang because it's an exclamation point. So you would actually pronounce this, this statement. So you pronounce the first statement x and y, the second statement x or y, and the third statement properly would be pronounced not x, but C programmers would call it bang x. Okay. And since x is true, this evaluates to the logical reverse of true, which is false. Okay. The other kind of thing we like to do in making logical decisions is compare things. So one other thing we need to talk about real quickly is how comparisons are done in C family languages. All comparisons all comparison statements that I'm about to show you return a bool type value. So you can either stick A less than B directly into an if statement, if A less than B, or you can assign it to a Boolean and say bool A is less equals A less than B. I actually don't need the parentheses there. I just always like to put them there to show that this comparison operation is happening first and the assignment operation is happening second. Okay, but that's not necessary because the comparison operator always takes higher precedence than the equals operator. Okay, so let's say we defined a series of integers A equals 10, B equals 12, C equals 10 again. Okay, if we look at the expression A less than B, okay, A is in fact less than B, so that's going to return a value of true. If we look at A less than or equal to C, okay, A equals C, so that also returns a true value. Okay, and we can do the same stuff with greater thans. A greater than B, A is less than B, so of course this would return a false value. And then we've got A greater than or equal to C. Again, A equals C, so this returns a true. What if we want to know if A equals B? Well, it would seem to make sense that we would just write, looking at all these other operators, A equals B, right? Wrong. This single equals is already used as the assignment statement in C++, so this statement has the effect of making A equal 12. Copies the value from B into A. That's not what we want, so that is not what we would do. In C, if we want to test if two things are equal, we use a double equals sign. So A equals B asks the question, does A equal B? And that, of course, is false, assuming we didn't already execute this statement that makes A 12. If A is still 10 and B is still 12, then A does not equal B. A equals C, they're both 10, so of course that's going to return true. And then lastly, we have a not variable. We can say if A bang equals or not equals B, A does not equal B, so that returns true. If we had A not equal C, well, they do equal each other, so that returns false. Okay. Two caveats here that you need to know about. One is that when comparing floating point numbers, that is types float or double, you almost never want to use the equals sign to check, because if you looked at, for example, bool should be equals 2.0 equals square root of 2 times square root of 2, okay, if we test for exact equals there, that's going to fail because there's just enough inaccuracy, enough rounding errors in calculating the square root of 2 that square root of 2 times square root of 2 would actually be something like 2.00000000004 or something like that. Okay. Point is, it doesn't exactly equal 2.0. So what we can do is we can say bool close enough equals absolute value of 2.0 minus square root of 2 times square root of 2 is less than, say, 1.0 e negative 9. Okay? So we're saying with 9 digits of accuracy, we're calling them equal. Okay? That's close enough for most engineering approximations, and that will do fine. Okay. The other caveat that's worth noting is that if you're working with non-numerical variables, if you're working with a string, for example, capital letters count as less than lowercase letters. If you said if 1 is less than James, okay, in a dictionary, JA comes before JU, so this should be false, but in the encoding, and see my lecture on advanced types, the way bytes and bits are encoded, or the way letters are encoded as bits, that's a smaller value than that by about 20. So about 28, something like that. So this would actually evaluate as true. So just be careful when you do comparisons of strings that less than doesn't always necessarily mean it comes first in the alphabet. Okay, so finally we've got all the basics down after 20 minutes. It's time to actually make a decision. So let's say you're writing a program, and at the end of your program you want it to say good day to your user, but you want this to be time specific. Okay, if it's bedtime, you want to say good night. If it's less than bedtime, you want to say just goodbye. Okay, we can represent that with a flow chart like I showed at the beginning of the program, like this. If T now is less than T bedtime, okay, if that's true, if it's true that it's less than bedtime, we want to say goodbye. If it's false, if it is at bedtime or later, we want to say good night. Okay. And then these streams would come back together and continue with the program, whatever the program needs to do to exit at that point. Okay, we might just put our end of our program right there. How do we make this in C++? We use the keyword if, and then a pair of parentheses around the condition we're testing. So let's say I have a now time, which represents the time that I just got from the system clock. Okay, if now time is less than bedtime, and we'll assume that the user has already communicated to us what bedtime is, or maybe the computer knows best and just knows when you should go to bed. If now time is less than bedtime, then we use a curly brace to set off a block of code, and we'll see out goodbye for now. Okay. Else, that is, so the if now time is less than bedtime, that took us down this branch here. Else, that's t now is not less than bedtime, that's going to take us down this other branch. So we need to write that code right here. So we put another set of curly braces to mark off another block of code, and this time we're going to see out good night, sleepyhead. Okay, so that's the basic structure of a C++ if else construct. That's how a decision is made in C, C++, Java, C#. I think that's how Apple's Swift uses decisions as well. So all works pretty well. Now, there are several more advanced ways to make decisions. Okay. First, let's take an example of take the same program, but now if it's between midnight and say 11 a.m., we want to say good morning. If it's between 11 a.m. and 1 p.m., we want to say good day. If it's between 1 p.m. and 6 p.m., we want to say good afternoon. If it's between 6 p.m. and bedtime, which we'll say is 10 p.m. for right now, we want to say good evening. And after 10 p.m., we want to say good night. Okay, we could put a whole bunch of if statements and say if time is greater than midnight and time is less than 11 a.m. Okay, we can do that. But if time is less than 11 and time is if time is greater than 11 and less than 1, okay, we could write this as if time greater than or equal to 11 a.m. and time less than 1 p.m. Okay. Then do day. If time greater than or equal to 1 p.m. and time less than 6 p.m. afternoon. Okay. We can do that. That's fairly complicated logic, and actually the main problem is it slows the computer down because the computer has to evaluate every single if statement, even if it found the first one to be true. Even if time was noon and it reads through here and says, yep, that's true, going to execute this. Well, now I'm forced to check if the time is greater than or equal to 1 p.m. and if the time is greater than 6 p.m. and if the time is greater than 10 p.m. Even though I've already done what I meant to do. So there is, I bet you can guess this, a better way. Okay. Like there ought to be a better way to erase the screen here. Okay. We can use an if-else chain. If now time less than 11 a.m. Okay, obviously I can't use 11 a.m. as a input in C++, so I'll define 11 a.m. somehow as end of morning. Okay. Then I can see out a string I've defined somewhere else called morning. Okay. But here's the key thing. I only had to do one comparison there because it's always greater than midnight. Midnight is 0. And it's, so I only need to check if it's end of morning. Now, I already know if I get to the else that it's past end of morning. So I don't need to check that again. Now all I have to do is say if, else, I follow my else with another if, else if, now time less than start of afternoon. Okay, then I'm going to see out my good day phrase. Okay, else if, now I've already checked that we're not in midnight to 11 a.m. or 11 a.m. to 1 p.m. So I can just go straight to the next comparison and say else if now time less than start of evening. Okay, I'll see out my afternoon phrase. So you see how this works? I could do another else if for less than bedtime, and then, okay, so I get else if now time less than bedtime, then I see out my evening phrase, and then my last one I don't even need to do a comparison because I've already found out that it's not midnight and it's not this and it's not this and it's not this. So if I reach this else, it has to be after 10 p.m. So I just see out my good night phrase. And this whole thing executes as one big decision block. Okay. Advanced decisions 2. Nested ifs. Okay. Let's say you're running a shipping company, okay, and you charge different rates based on where the box is going. Okay. So we might say in the US, yes, no, okay. Alaska or Hawaii, yes. Well, they're more expensive than sending it just next door to Alabama, okay. Over here, we might ask overseas, okay. If we're shipping next door to Canada, that's not as bad as shipping to Timbuktu, okay. This is what we call a nested decision. You make one decision here, and then that leads immediately to another decision that is what we call nested inside this other decision, like little Russian nesting dolls. One fits inside the other. Well, the way we express this in C++ is with nested ifs. So if destination in US, okay, I'm assuming I've defined a Boolean somewhere in my program before now that knows if the destination is in the US, okay. So that block gets me this far, but now I need another if. So I indent and I say if AK or HI, Alaska or Hawaii, okay. Then I put in my code rate equals rate 1, okay. Else, now I have to check what is my else communicating with here. This else goes with this if Alaska or Hawaii. So what I'm saying else here is I'm in one of the other 48 states. So rate equals, so we'll say this rate is US high, and this rate is US low. Okay, now I put in the else for my first if, okay, and here that's taken me to this if. So if is overseas, then I'm going to say rate equals non-US high, else, and this else goes with my if overseas. So this is going to be not overseas, so rate equals non-US low. Now you may have noticed in this example I didn't use the squiggly curly braces. Why? Because I had a very limited amount of space. If you have only one statement after an if, you can get away with not using curly braces. It's better to use them. So the way this should look is if dest in US, also I suck at drawing curly braces, else, okay, and then this if would get its own set of curly braces, the else would get a set of curly braces, and so forth, and so on. Okay, that actually makes your code look a lot easier to read, because if you line up all these curly braces, it's pretty clear which if goes with which else, and so forth and so on. Okay, advanced decisions 3. Sometimes the if we want to do is something as simple as if A is less than B, least equals A, else least equals B. You can tell, hopefully from inspection, that this is a very simple piece of code for finding the minimum or the lesser of two numbers. We can do this. C++, C, Java, C#, all give us the option to do this in a single line of code by saying least equals X, or we're using A less than B question mark A colon B. Okay. What this does is this tells the computer to check this for true or false. Okay. And then if it's true, this value is assigned to least. If it's false, then this value is assigned to least. Okay? Some programmers find this incredibly confusing. Other programmers find that it saves a lot of typing and can even make your code appear more compact and more organized. Okay, finally, advanced decisions 4. Switch case and default. Going back to our first problem of saying hello, saying morning, good evening, whatever. That's a classic kind of decision for a switch statement if you can reduce everything to single integer cases. Okay? And the way a switch statement works is you say switch, and then you indicate what value you want to switch on. And it has to be either an integer, an int type, or a character. Okay, and that's a single character like A, B, C, D, not a string of text. Now Java and C# have elaborated the switch statement, and they allow more interesting comparisons to be done in the switch, but the basic C and C++ variant works like this. So if I take my now time, let's say it's expressed in military time, so now time is something like 12:30. Okay, I'm going to take now time and divide by 100. It's an integer, so dividing by 100 lops off the 30, and what I've got left is this 12. Okay, so that's what I'm going to be switching on, is now time over 100. Okay, then I open curly and I start providing cases. Case 0. Okay, that would be midnight to 00:59. Okay, I can group that with case 1, case 2, and I can keep doing this, ... all the way down to case 10, because we decided that 11 was when we wanted to start saying good day instead. Now I provide my code, no curlies here, see out the statement I wrote for morning, the string that I've got there for morning, and then I put a very important keyword, break. Okay, and that break is going to follow me all the way down to the end of the switch statement and kick me out. Okay. Now, proper style has the cases stacked like I've just shown it here, but you can also stick them all in one line. Case 11, double space, case 12. So that groups 11 to noon and noon to 1 into one group. See out my good day phrase. Okay, and again, very important that I put in a break. If you don't put in these break statements, it will just keep running down the next set of statements and the next set of statements and the next set of statements. So I can have case 13, case 14, on to, I think we said 5 p.m., so that's 17 would be the end of the afternoon. See out my afternoon phrase. Okay, I'm going to have to take this whole thing and wrap it around so that I can finish my switch statement. I've got the cases. I've got to have a break here. Okay, I'm going to have the cases for evening, 18, case 19, case 20. Let's say for the sake of not having to write as much, that this person has a pretty early bedtime. So I've got all of my evening times, and then finally I put in a default case. This is what the program does if it falls through every other case and doesn't match any of them. So the default is that we're going to be, if we didn't find any of the other times, then by default we're after bedtime. So I'm going to say my bedtime phrase and break. And then that ends my switch. Okay. Some programmers find switch to be cumbersome and difficult to use, and they don't like it at all. Other programmers find that this is absolutely fantastic. If I were writing a calculator program, for example, and I wanted to know if the person typed plus, minus, times, or divided by, I'd do case plus, case minus, case times, case divided by, and then I've got my 4-function calculator right there without having to write a complicated series of ifs and elses. Okay, finally I want to sum up with a few best practices and common pitfalls. First, a common pitfall. Don't end an if or else line with a semicolon. Okay, if you were to type if A less than B semicolon, and then your next line was to to call the function pick A. Okay. And then you were to put else semicolon pick B, guess what would happen? The program would read through, if A less than B, what does it want me to do? It wants me to do an empty statement. Well, kind of odd that the programmer wants me to do nothing here, but that's what they said, so I'm going to go with it. And then it's going to execute pick all. This statement will run no matter what. Okay? And then it's going to see else, and what's it going to do there? Well, it's going to throw up a compiler error because else is no longer associated with an if. The if is already complete and we moved on. Okay, so this whole thing fails because of this semicolon and that semicolon. So be sure to end every statement line with a semicolon, but not your ifs and elses. Okay. A best practice here, use bool variables to store values. Okay, so if I'm writing a self-driving car program, it might run through a whole bunch of checks every second, and one of those checks might be, is light green? Or again, to put it in that positive syntax we've been using, light is green equals, maybe I have a routine called get light color, and it comes out equaling color green. Okay, and now we can go on and do several other things, several other lines of code, and then get to the key point where we say if light is green, full speed ahead. Okay, so using this bool variable means I can capture this comparison here and then stick it into my if later on. I don't have to call get light color a second time later on. Okay, so that's a good best practice to follow when writing complicated programs that keep track of a lot of variables, or a lot of true-false values, a lot of comparisons. As we've said in the past, avoid magic numbers. It's better to say if time less than bedtime than to say if time less than 2100 hours in military time. Okay, for two reasons. One, much clearer here. It's clear what this means. Whereas here, the user is asked, another programmer, yourself, a year later, is asking, what is this? The other thing is, if I define bedtime as a variable, or a constant or something, then I can change it much more easily by searching for bedtime in my code and changing that, or I can even make it something that the user can see in as part of my program. I can say see in bedtime and then know when the user goes to bed instead of just assuming. Okay. Don't confuse equal and double equal. Okay. C++ will actually compile fine if you say if A equals B, blah, blah, blah. Okay. That will compile. What will happen when it gets to this is it will assign the value of B to A, and then it will treat A as a Boolean variable. That is, if it equals 0, the statement is false. If it equals 1 or any other number really, the statement is true. That's not what you probably wanted. So always check those and be sure that you said if A double equals B instead. Okay. Common programmer mistake. Only put what needs to be ifed in the curlies. Okay. So like if I were writing a calculator program, as I mentioned earlier, if opper equals plus output plus equals input. And I'm tempted to put here a cout output, but then when I say else if operator equals minus, got output minus equals input, and another cout output. What did I do wrong here? Well, for one thing, I forgot my curlies. Keep doing that. Okay. But what I really did wrong here is I took a statement that I'm going to do whatever operator turns out to be, and I put it in the if and I put it in the else if. A better way to write this is if output plus equals blah, else if output plus equals blah, and then after all of my statements are done, I can put here cout output. Why is that better? Well, fewer lines of code to maintain, for one thing. But also less chance of making a mistake. That I might type a cout somewhere and type cow instead somewhere else, and you have to hunt that down. But the last reason is that if I ever want to change what my output looks like, here I only have to change the output once. This first way, I have to hunt down every output statement and change it. So much easier to maintain this code over here than that code there. Okay, almost done. Last bit is we want to, something that I've been demonstrating this whole time, but haven't really explained. You want to indent code inside ifs and else's and align your curly braces. Okay, so it should say if blah open curly, then indent, do something, close curly. And this helps me track which pieces of code I intended to be inside the if clause and which pieces of code now are clearly not part of the if. Okay. Okay. All right. I think that is about the end of what we need to do with ifs and else's. Thank you for watching, and please stay tuned as I get us into loops next time.